Yeah, so those who know me probably know I usually talk only about Apache Fleet, which is a system of pre-committing for the last 3-4 years. But today I'm happy to announce to you our very new ambitious project. And it's, spoiler alert, this is a new system architecture that enables data processing to be both complex and time critical. And what do I mean by that? Well, data processing is already important for decision making. We use data processing, for example, with IoT systems to infer whether it's raining or it's cold from sensor events, or do something more sophisticated than this, such as creating models that we use for recommender systems. Auto driving cars use camera feeds to infer whether someone is crossing the street, though that doesn't always work, as you know. And more and more sophisticated things. And of course, knowledge is important for decision making because then we can take action. If it's cold, we can turn the heating on. If a credit fraud is detected, we cancel those transactions, and so on. So that's the idea. But as you see here, there are different types of knowledge, right? There's knowledge that is time critical, and knowledge that is complex and less complex. So we could just go ahead and classify knowledge based on complexity. Complexity usually in data processing means that there are a lot of data dependencies in the computation to extract knowledge. And time criticality means how urgently we need that knowledge to take decisions. Okay. And behind those examples I mentioned, there are specific data processing models. This is not an exhaustive list, but here you just get an idea of what implements, what type of data processing implements that knowledge. And behind that, there are specific system architectures and platforms that implement these models efficiently for the right hardware. There are two trends here. For managers here, the more you go towards the top right, the more expensive it gets, because you have to basically buy GPUs or basic processing units. Another trend I see is that systems that are complex but not so time critical, and vice versa, platforms that are for time critical computation but not so complex, like stream processing, they don't really utilize hardware well. They just run, they're implemented in an application language like Java, and they just do basically what is needed without utilizing the available modern hardware so well. So what we want to do with continuous deep analytics is to cut through all these different system platforms and categories and try to offer seamless execution of all these different data processing models and utilize the hardware well. And why is this important? We have been observing more and more recently that modern data pipelines need to combine many diverse workloads. So you probably need to do something like feature learning in your pipeline and use tensor programming, then combine it, join it with a data stream or a database using relational data streams, and probably you might need to encode and analyze your data as a graph, so you need dynamic graphs, and so on. These are just some examples, right? So pipelines are really complex nowadays, if you want to provide critical decision making, you have to be efficient, combining all these different workloads. Hardware acceleration using GPUs and TPUs is important, yes, but it's not enough. We have to do more. And the problem that we see here is that, okay, some computation might be running in GPUs, some computation in tertiary tasks, and some computation in stream processing tasks or databases, but we still need to share computation across these different frameworks and do this efficiently. There's no really common way to share computation, and usually we have to do a lot of data exchange, which is very expensive to disk. And here I can show you how this can be done more efficiently. The idea is called computation sharing. Let's say we have two functions that are data dependent in the pipeline, f and f prime. And typically we would have to pass intermediate results from one function to the other, one computation to the other, through copying data into memory, passing to the network, or writing to disk. But since this takes a lot of time, what we could do instead is to fuse those functions together. So run this computation together without unnecessary need to transfer data around. This provides less data bytes and no additional overhead. And we believe that the combination of hardware acceleration and optimized, efficient computation sharing can really offer future systems and pipelines critical decision making, the ability to take decisions fast, right? Because we get results faster. The problem right now to implement this is that all these different computation models are implemented in different frameworks, written in different languages, and having no common layer to actually fuse this computation together. So if I, for example, write a linear regression model in TensorFlow in Python, and I want to join that with a relational string and link and using Scala, there's no really common way to do that. It's like oranges and apples, right? So how do we do that? And we see that the big picture here, there are so many systems and different frameworks for each type of computation. You see here in streaming, there are like 8 systems. For graph processing, there are like machine learning, there are like 20 different solutions and models, and things are very complicated. We can't create pipelines that are efficient across this stack. But the solution is quite clear to us. We believe that the way to solve this problem is to come up with an intermediate representation. A common way to describe computation and data and translate computation across all these different computational models to that representation, and then do all sorts of optimizations and hardware acceleration on that layer. We didn't just wake up with this idea. Of course, there are efforts going on in this direction. One of them is the Weld intermediate representation at Stanford that is made by Matei Zaharia, the Spark architect. The idea with Weld is a very good example of what you can do with an IR. Weld basically translates computation across all these different frameworks and more into a series of operations using model comprehensions. And then it optimizes the code so well and runs into the right hardware in a way that is even better than doing all these optimizations by hand, basically. And it's also generalized. Unfortunately, Weld is only limited right now to short task execution, so it's not really for continued real-time processing. But it is getting there. There's also another project by Facebook that might have heard, the tensor comprehensions. This is limited to tensor operations, as the name suggests, and execution in CUDA. But what I really like about this solution is that they use an IR to also do online optimization. So they have something like a just-in-time compiler that takes matrix operations and does alternative executions to improve the performance. So what we want to do is basically something even more general. We want to allow different data processing models in our application, in our pipeline, and also different languages. Okay, we want to fuse them together and provide a platform where you can actually execute all these different tasks efficiently. And of course, you won't be able to provide different hardware to your workers, so the system will be able to adjust the computation to the hardware that you provide. Of course, we'll go with an IR, so the application will be compiled to intermediate representation. We'll do all these computation sharing optimizations in the compilation step, and then also do additional physical optimizations on top, since we know the hardware that we're running. And on top of that, we'll also allow for runtime optimizations to a distributed zip compilation step. And we have the right professional people to achieve that. We have a world-class team of scientists from RISE 6 and KTH, and we're growing. We have really skillful master students that are working with us right now. And we believe that we will reach our goal pretty soon, so we might have a prototype by next year. This is just a preview. And of course, we have a poster later, so you can pass by and we're going to answer all your questions.